Yeah.
Yeah, okay, so let's welcome Ryohei Kobayashi from the Tokyo University. So we first thank him for giving this talk during this I believe it's midnight in Japan. So it's already very late for him. So he has done many work in SPT and TQFT construction. So today he's going to give a talk about his recent work on the construction of topological superconductor with time reversal symmetry in 3+1D. So please start.
Yeah, thank you for introduction, your and organization. Let me share screen. So can you see the slide?
Yes.
Okay. So thank you for giving me a great opportunity to speak here. This is Ryohei Kobayashi from the University of Tokyo. Today I'll talk about the physics of the interacting fermionic phases of fermions. This talk is based on my recent papers on arXiv listed as follows. So feel free to look into these papers if you are interested in. So here is the outline of my talk. In this talk, I will first introduce path integral formulation of the fermionic phases of matter on Lattice, which is applicable for phases with time reversal symmetries, and then discuss physical applications to the construction of gapped boundaries of the fermionic SPT phases based on our path integral description. And I will also refer to the application to the 1+1 dimensional topological superconductor, and finally talk about the exactly solvable model for the 3+1 dimensional topological superconductor based on my recent papers, if time permits. During these projects, I would like to thank for Kantaro Omori in Simon Center and Shinsei Ryu in Princeton and Yuji Tachikawa in IPMU for the enlightening conversations and collaborations. So then let me start with the introductory slide. The scope of this talk will be the topological phases of matter. Such phases cannot be characterized by a local proof, but rather can be diagnosed by making up boundaries and looking at edge physics, or it can be diagnosed by putting the system on the surface with non-trivial topology. One well-known example is the fractional quantum Hall states, where we can observe the chiral edge modes on the boundaries, or we can also observe some non-trivial clandestine degeneracy once we put the system on the surface with non-zero genus. So the topological phases with these properties are captured by the effective field theory, which is called the topological quantum field theory. For instance, the Chern-Simons type theory effectively describes quantum Hall states. So in this talk, I will be interested in such topological phases, which can contain the fermionic degrees of freedom. And especially, we are interested in this talk, we are interested in interacting phases rather than free fermionic phases. One reason is that the classification of the interacting fermionic phases generally differs from the free fermionic phases. The seminal example for such a difference is that the 1+1 dimensional fermionic SPT phases in cross PD1 that corresponds to the time reversal symmetry with time reversal squared 1. In this case, we observe the Z classification in free fermionic phases, but it breaks down into the Z8 by the effect of interactions. And
could I ask you a question? This is Shankar Sharma. May I ask you a quick question?
Yeah.
Why are you saying Kita is in class BD1? I mean, it can be, but it doesn't have to be, right? It depends on whether you make the order parameter complex or real. It could be class D. It could be class D also, right?
Yeah, I'm just saying that once we enforce the time reversal symmetry, it's regarded as a SPT phase is protected by time reversal symmetry. Then
sure.
It's classified by Z8.
That's absolutely correct. But I think your statement will apply even if you take a slightly more general situation with class D, right? Because there are other.
Once we allow for some perturbation which can break the time reversal symmetry. It's no longer Z8. It's just
Okay.
Z2. Yeah, it's just
Okay.
Z2.
Right.
Yeah.
Oh, it's a minor question. Go on.
Yeah. Yeah. Thank you for question. So this Z8 classification is generated by topological superconductor, which is known as the Kita wire. And the one of the important questions regarding the SPT phases is for a given definition, some local definition of SPT phases, which can be given by a space-time path integral or Hamiltonian, how we can actually figure out what phase the given system is in. So this problem is in general hard, as hard as solving the interacting Hamiltonian itself, but in principle, the conventional answer to such a question is to couple with the background gauge field, see the response to the gauge field of the symmetry, so that we can figure out what's the effective action for the SPT phases. The background gauge field is typically realized as a twisted boundary condition with respect to the symmetry when the symmetry is on side, which amounts to inserting symmetry defects in spacetime. Especially in the case that if the symmetry reverses the orientation of the spacetime, such as a time reversal symmetry, the background gauge field is realized by considering the unoriented spacetime because it naturally encodes the orientation reversing defect in the spacetime. So actually, in the case of the 1+1 dimensional topological superconductor, we expect that we can extract some the Z8 classification of the topological superconductor by evaluating the partition function on a 2-dimensional real projective space, which is actually unoriented, according to the some classification scheme of SPT phases based on the cobordism theory proposed by Kapustin. But in the first place, it's highly non-trivial how we actually define the local path integral for SPT phases on unoriented spacetime, and it's also non-trivial how we extract the information of such responses from a given Hamiltonian wave function. So it's important to establish some local lattice definition of fermionic topological phases on either oriented or unoriented spacetime in order to make sense of the responses to the time reversal gauge field. And I would like to begin with providing such a formalism in this talk. So let me talk about some lattice construction of the fermionic topological phases. The interacting fermionic SPT phases on a lattice system is initially proposed by Gu and Wen. They described the subclass of some fermionic SPT phases protected by time reversal symmetry, protected by on-site symmetry in terms of the path integral over Grassmann variables. And this path integral by Gu and Wen is later promoted to partition function of some specific topological field theory by Gaiotto and Kapustin. And then it turns out to provide a quantized topological invariant defined on the spacetime. So for our purpose, it's good to extend these constructions to unoriented manifolds in order to discuss the time reversal topological phases. So Gu and Wen use Grassmann integral to describe such topological phases, and their Grassmann integral is written as sigma as a function of alpha. Here, the M is some d-dimensional space-time equipped with a triangulation, and alpha is a Z2 field, which is defined on the d-1 simplex. So in the case of the 2-dimension, so M is just a 2-dimensional surface which is triangulated, and alpha is a Z2 field defined on the 1 simplex, just an edge. And we can also think of alpha as some background gauge field for some Z2 symmetry, d-2 form symmetry, if one is familiar with a higher form symmetry. Then the degrees of freedom in the theory is represented by a pair of the Grassmann variables, theta and theta bar, introduced on each d-1 simplex. if and only if the alpha is non-zero on it. So we have some configuration of alpha, and we put the pair of Grassmann variables if and only if the alpha is non-zero on it. So for example, if we consider two-dimensional, we put a pair of Grassmann variables on each edge for non-zero alpha. Then the action is expressed as a path integral of these Grassmann variables put on the spacetime. So we will, in general, consider unoriented spacetime manifolds. So let me comment on how we make up the unoriented spacetime. So unoriented spacetime is constructed by gluing a local coordinate system with the transition function reversing the orientation. This is regarded as the reversing the orientation once we go across the codimension 1 defect, which we call the orientation reversing wall. That reverses the orientation, and so yeah, so which we call the orientation reversing wall, that is represented as a red line in this figure. So then the Grassmann integral is defined like this. It consists of the measure of the integrand part of the path integral. So the Grassmann integral runs over the all the Grassmann variables in the spacetime, and the integrand is expressed as a product of the local weight supported on each D simplex. So here the local weight is given by the product of the Grassmann variables contained in a single D simplex. So for example, in 2 dimension, in this figure, it is a product of Grassmann variables in a triangle. So, and finally, the action also has a term which appears only in the case of the unoriented spacetime. This term in the pink rectangle assigns plus I or minus I phase factor on a pair of Grassmann variables located on the orientation reversing wall. So
sorry, I have a question about that. Was it plus I or minus I, or you're saying it doesn't matter?
Yeah, it has some specific canonical rule to assign such a sign, but yeah, that's kind of detail. But yeah, this depends on the sign of the simplex. We have this. Yeah, this model is based on some barycentric subdivision, and we assign plus or minus sign on each D simplex with respect to the branching structure on it. And if the orientation reversing wall is adjacent to the D simplex, which has a sign plus, we assign plus I, and otherwise we assign minus I. But yeah, it's kind of detail. Yeah.
Thank you.
Yeah. So then let's refer to the important property of the Grassmann integral. So the action computes phase for a given configuration of alpha, Z2 field alpha, and it turns out that this phase is this computational result is, or this action is not a linear function of alpha, but a quadratic function of alpha. This property is understood by explicitly comparing the sigma of alpha plus alpha prime and sigma alpha times sigma alpha prime, which will be the same if the phase were linear. But these two are actually different. To compare these two expressions, we bring the form of the right-hand side into the left-hand side by permuting the Grassmann variables contained in the measure and the integrand. Yeah, so both sigma alpha and sigma alpha prime is some sequence of Grassmann variables. So, and we can bring the form to the left-hand side by basically by permuting Grassmann variables contained in measures and integrands. And this permuting process splits some non-trivial fermionic sign because of the anti-commutativity of the Grassmann variables, and it makes these expressions different. And moreover, we also have a plus sign, minus sign factor. This also makes two expressions different. For example, if both alpha and alpha prime are non-zero on some d-1 simplex E, then if you have some such a sign factor on such a non-zero simplex, then the sigma alpha and sigma alpha prime both has a contribution of plus I or minus I, which will be the same. And while the sigma of alpha plus alpha prime is 1 because it 1 plus 1 is 0, and it doesn't have such a sign factor. So we are comparing the 1 and I times I, which is minus I. So these two are different. So yeah, we have such a contributions which makes difference between these two expressions. So, and by explicitly computing these phase differences, we find that the total phase factor is summarized in kind of neat fashion by using some operations called the higher cap product defined for this Cauchy field alpha. And we call this relation as a quadratic property of the Grassmann integral.
Can I ask you a couple questions? So
yeah.
Can you give maybe first some intuition for where this expression is coming from, where you get it? Why should we consider this? Do you have anything to say?
So you're asking the reason for considering such quadratic property?
No. Just be the top line. You define this Grassmann integral.
Yeah.
So far, the way you've defined it, it seems a bit mysterious. Where did it come from? Like, why did we define it like this? Do you have any intuition to give about that? Like, is this sigma? I mean, maybe it's another question then is, like, we have a triangulation of this manifold M.
Yeah.
Is sigma independent of the triangulation? Like, is this retriangulation invariance?
Actually, it's not, as I explain later. But after coupling the spin structure or pin structure, it actually becomes invariant. Yeah.
So on the left-hand side, so this thing is actually a function of M, alpha, and the triangulation.
Yeah, it depends on triangulation. Yeah.
Okay. Yeah, I mean, if you have any more intuition to give, it'd be great. Because I think for many people, this is probably mysterious. Like, where does this come from?
Yeah, I agree.
Kind of could I expand on Mesam's question, although I know nothing about the subject? I mean, I think the question basically boils down to your definition, what you are calling the phase for this theory. Phase always has some indeterminate factor there, and here it may be the triangulation. So once you call something the phase, you have some freedom in defining what you're defining. And I think that's what the question boils down to. So perhaps you can give some intuition why we should accept this particular equation as the phase for this theory. You have some freedom in defining a phase, but it looks like the phase depends on triangulation. So I think that's what I interpret Mesam's question as meaning that.
Yeah, the meaning of phase is that so this is the path integral of Grassmann variables. So it's basically in the form of integral of d theta of theta, but the order of the Grassmann variables in the d theta and of the measure and integrants are different. So this fits some sign. But by the phase, I just mean the computation result of this path integral.
Okay, I think you should go on because I think you'll discuss this quantity more down the line. Okay.
Well, let me add one small thing. Like this, the fact that you put an I there, right? that
Yeah.
because when you go around the orientation reversing wall twice, that means that you pick up a minus sign. So the intuition for the plus or minus I factor is because you want two reflections to be -1, which is related to the fact that you have a pin minus structure.
Yes,
Which is related to
yes, that's correct. Yeah.
+1.
Oh, okay, that's good. That then answers my question also.
That's where the I comes from.
Okay.
Yeah. Yeah. Thanks for explanation. Yeah.
Yeah. So these kinds of things, just kind of intuition for why you know the various terms appear they do, is always helpful for this.
Yeah. Thank you. Yeah. About the non-invariance under the triangulation, I can explain shortly. So what? Sorry. So the quadratic property of the Grassmann integral actually has an important physical consequence. So if we consider the gauge transformation, which shifts alpha by coboundary, we observe that this theory is not invariant under the gauge transformation because of the quadratic property, and such a phase ambiguity under the gauge transformation is this is read by quadratic property, and here if we consider the alpha as a background gauge field for the dimensional form symmetry, the phase ambiguity is regarded as some sort of the quantum anomaly, fifth anomaly of this theory, which dictates that it's not invariant under the gauge transformation of the background gauge field. And when the theory is anomalous under the gauge transformation, we can restore the gauge invariance by coupling with the SPT action in higher dimension. By evaluating the phase ambiguity, the bulk SPT action turns out to be expressed like this. And here, a W2 and the W1 is a specific quotient which represents the second and first steepest Horton class of the spacetime, respectively, and this SQ2 operation is called the Steinrod square, which is expressed as a higher cap product, and this dictates some non-invariance of the sigma under triangulations because if you retriangulate the theory, the variation of this theory is controlled by let's compare the two theories based on the different triangulation, and then we can basically interpolate these two theory using the d plus one dimensional bulk, and the difference between these two different triangulation is controlled by evaluating this d plus one dimensional action on the interpolating d plus one dimensional bulk, and such a phase makes difference when we try to evaluate the retriangulation of this theory. And after these preparations, we can talk about the large subclass of the fermionic SPT phases, which is called the Guen phases. So let me start with describing the 1 plus 1 dimensional SPT phases. So it's possible to generalize for more higher spacetime dimensions. It's well known that bosonic SPT phases are labeled by group cohomology. And similar to the bosonic case, the fermionic Guen phases are also represented by some cohomological data. And in 1 plus 1 dimension, the Guen phase contains the data of the first cohomology, which takes a value in Z2. So G is our symmetry, and Cohen phase is represented as this data of first cohomology. Then we can express the Cohen fermionic SPT phases using the Grassmann integral. In the Grassmann integral, the first cocycle M just works as one from Z2 field, which determines the location of Grassmann variables. So we can think of M as alpha, which is used to define the Grassmann variables, Grassmann integral. So the action is just given by evaluating the Grassmann integral based on this Cohen data M. And as we have seen in the previous slide, this Grassmann integral is anomalous on its own, so it's not invariant under the gauge transformation and the retriangulations. But in 1+1 dimension, the Steinrod square of the one cocycle is known to be 0, so we can ignore this term. So the non-invariance, so the anomaly is controlled by the term, which involves the Stiefel-Houtny class. But if we know that this Stiefel-Houtny class, W2 plus W1 square is cohomologically trivial in a given spacetime, we can make the action completely gauge invariant and retriangulation invariant by introducing one cochain, eta, which trivializes Stiefel-Houtny class. So I mean, the derivative of eta is, so we prepared some cochain eta whose derivative is W2 plus W1 square. Then we can prepare some term, some content term, which depends on eta. And by coupling such a term with respect to eta, we can construct a non-anomalous topological invariant. And this theory works as some topological invariant, and now depends on the Cohen data M and eta. And we have seen that a Cohen phase requires some cochain which trivialize Stiefel-Houtny class W2 plus W1 square. Here we know that for example, in the case of the oriented case, the W2 second Stiefel-Houtny class works as a obstruction class for the spin structure for the spacetime, and the spin structure is required for Lorentz invariant theory of fermions, and that makes possible for fermions to transform as a spinor under the Lorentz symmetry. And in the continuum spacetime, the spin structure is defined as a way to lift the orthonormal frame to spinor bundle, and such a lift is possible if and only if the obstruction class is vanishing. But from the unoriented spacetime, there is also an analog of the spin structure called the pin plus or pin minus structure, that is related to two kinds of possible patterns for the double cover for lifting the orthonormal group to the spinor group. And so here physically the pin minus structure amounts to the time reversal squares to 1 and pin plus to the time reversal squares to the fermion parity respectively. But on the lattice of the triangulated spacetime, spin or pin structure is specified by a choice of the one cochain that trivializes obstruction class. So in our case, eta is regarded as a specific pin minus structure on the lattice because W2 and plus W1 square is obstruction for the pin minus structure. So thus we have formulated it by using the Grassmann integral 1+1 dimensional Cohen phase as the topological invariant of the P minus surface, or more precisely a partition function of the P minus topological theory on the lattice. And such a construction is also possible in higher dimensions. in generic case, the Guen phase with a p minus structure in t plus 1 space-time dimension is specified by a pair of cohomological data x of d plus 1 and m of d. In E1 plus 1 d, I just wrote m in the slide, but in generic dimension we take advantage of these two data. And in 1 plus 1 d, these two cohomological data are independent because standard square is 0. But in generic dimensions, these two data are correlated because these two data are subject to the equation which is called the Guen equation. So the derivative of x becomes the standard square of m. And because of the Guen equation, if we try to give the action by the integrating x of t plus 1 over the spacetime, because the x is not closed, it becomes anomalous. It becomes a triangulation non-invariant and characterized by Baroque SPT action, standard square of m. But we can cure such a non-invariance by coupling with the Grassmann integral and the p minus structure. So after all, the theory is written like this. So this theory has an anomaly of standard square, and this theory has an anomaly of standard square plus Steve-Hoytnik cup m, and this theory has an anomaly of standard Steve-Hoytnik cup m, and so this expression is completely cancels the anomaly, and it's fully invariant under the gauge transformation retriangulation. So using such Guen data, we can obtain the SPT action for the Guen phases, and which is expressed as a topological invariance. So, and we can regard this as a Guen SPT phase, which is based on the p minus structure. So this is a formulation of the Guen phases, and by using such formulations, we can move to the application of our path integral formalism.
Can I ask a quick question?
Yeah.
Previously, your theories were all G0 cross Z2R.
Yeah.
If the G0 and the Z2R are actually coupled, like that's some kind of semi-direct product, or even more general than that, then do we have a formalism to know what to do?
Yeah. So in this case, in the case of the twisted product, I think that so it's no longer p minus or p plus, and because the on-site symmetry is not really coupled, so the obstruction class is also changed. And so, for example, we in general have some W2 plus W1 square plus some second cohomology of the on-site symmetry, and then so eta is chosen as a trivialization of such obstruction class. But yeah, we can still use the Grassmann integral to express such a phase. But
I see.
Because of the change of the definition of eta, the Guen equation is changed. Yeah, we have additional term.
Okay. Yeah. So it's known how to generalize it then.
Yeah. We know how to generalize.
Is it guaranteed the abstraction case can be trivialized? For example,
sorry.
Is it guaranteed? But here we have the W2 plus W1 square. So on some P minus manifold, it can be written as some delta eta. So if we have another two cycle, it may not be trivialized, right? Or it's guaranteed.
You mean what dimension?
So for example, you have the G0 semi-direct product with the some Z2. So you modify the Guen equation. So you have additional two cycle somehow. So
yeah.
How do you trivialize this case?
So your question is if the Gui question is guaranteed to be solvable.
Yeah,
it has a in the first answer, yeah, I don't know, about whether, it's possible, it has a solution or not.
Okay, so it's like given a solution, we can construct the partition function.
Yeah, given a solution, we can construct. Yeah.
Is it clear what the Z2 fermion symmetry is actually like? What that action is actually looks like in these, like in this model?
So you mean fermion parity symmetry?
Yeah.
So if you try to consider some symmetry defect of a fermion parity, it amounts to changing the definition of eta. So we are defining eta as some trivialization of W2 plus W1 square, but so eta has a multiple solutions which can be shifted by, for example, in the case of the 1 plus 1 dimension, it can be shifted by some first cohomology. But so it has it can have multiple solution, and this corresponds to the multiple choice of the spin structure, which which can be periodic or anti-periodic with respect to the fermion parity symmetry, or in the language of the spin structure, it can be Neveu-Swartz or Ramond, and inserting the defect of fermion parity symmetry amounts to changing the spin structure, in this formalism.
Thanks.
Yeah.
I have a question. Sorry, Sri, were you following up on that?
Yeah. I was wondering if they're like for if you have like a G symmetry, right? You have these like labels on the simplices that are labeled by G, and then there's some like G action on these labels. Is there some similar like Z2F action? Or
sorry.
Is there like a similar like, so this like G0 action, there's like labels on the simplices that are labeled by some group elements, and this group action, there's like a group action on those labels. Is there like a similar action for Z2F?
Yeah, I think so. To talk about the Z2 action. So we can basically consider the Hilbert space or by putting this theory on the space-time with boundary. Then it gives some wave function which is defined on the boundary, and so the boundary wave function is basically expressed as some fermionic Fock space, because if you put the boundary like this, for the Fock space with odd fermion parity is found here. So if the Grassmann variables is non-zero on boundary, it has an odd fermion parity. So basically, the fermion parity action is given by splitting -1, where the Grassmann variables is odd, but it acts trivial. It acts trivially when the Grassmann variable is not living on it.
Okay, so it's basically like an action on the boundary.
Sorry?
It's like a boundary action, you can say.
Yeah, I was talking about the action of the fermion parity on the Hilbert space of this theory. Yeah.
I have a quick question for your sigma here. So do we assume that alpha to be some closed closed form? Because if it's closed, we can imagine this alpha describe the wall line of the fermion. So, but if it's not closed, what does this alpha? What's the meaning of this alpha?
So if alpha is not closed, so alpha puts some line of alpha draws some line of Grassmann variables on this picture, but if alpha is not closed, this line is no longer a closed line, so it has an endpoint, and on the endpoint we have a auto fermion parity, and so such a auto fermion parity makes difficult to define such a Grassmann integral in as a local action, because so if the integrand is no longer so in this case the integrand becomes Grassmann out, so UT can become a Grassmann out, so it can have it's no longer local because it can anti-commute with another action away from the another action away from the where the Grassmann variables are out. But yeah, so yeah, we can also deal with a case where alpha is not closed if we talk about the gapped boundary of theory, gapped boundary of some fermionic SPT phases. Yeah, in this case, the endpoint of some line of Grassmann variables can escape to the bulk, and once we couple the bulk with boundary, it completely works as some local theory of fermions. Yeah, so yeah, such situation can appear in the bulk boundary coupled system.
So I wanted to ask a question also.
Yeah.
Maybe it's, I don't know, it's a quick question. So when you wrote your symmetry, like G0 cross Z2R or whatever, is that implicitly like you're not including Z2F as part of the symmetry, like you're modding out by Z2F when you write G as you did over there?
So in this case, we are not considering the twisted product between the on-site symmetry and fermion parity. So it doesn't contain the fermion parity.
So where is fermion parity? It's just somehow it's there implicitly because you're assuming R squares to.
Yeah, maybe I should have written as a D2F times G0 times Z2R. Yeah.
Okay, so here it's Z2F is kind of decoupled from this.
Yeah. In this case, it's decoupled.
But then if Z2F actually is coupled to it, like you have some twisted product or something.
Yes.
Then you also know how to deal with that.
So it's basically same as the twisted product we have talked about. So it's basically changes the definition of beta, and it also changes some Kuhn equation in a way coupled with some space-time symmetry. Yeah.
Okay.
Other questions? Yeah. So let's move to the application of our path integral formalism. So an interesting application, I think, an interesting application of our path integral formalism is to construct a symmetry preserving gapped phases on the boundary of the fermionic SPT phases. So in general, the boundary of SPT phases suffers from the fifth anomaly. The anomalous theory has a non-trivial low energy spectrum because it has to match the anomaly in low energy, and so it cannot be a trivial insulator at the low energy. There are possible fates of the low energy spectrum listed here. So if the theory is anomalous, it can be gapless, or if gapped, for the case of the discrete symmetry, the symmetry may be spontaneously broken. But the most exotic possibility for the spectrum is that gapped phases without the spontaneous symmetry breaking, which is typically realized as a topological ordered state enriched by a global symmetry. Then let's ask the following question. For a given SPT phase, does the SPT admit the symmetry preserving topological ordered state on the boundary? So in this case, if the boundary has a 1+1 dimension, this last possibility is not possible because there is no topological order in 1+1 dimension. So the question is for boundary with these dimensions equal or more than 2+1D. And for the boundary with space-time dimensions equal or more than 2+1D, there is a positive result for the bosonic SPT phases by proposed by Witten. According to them, the bosonic SPT phases protected by a unitary on-site symmetry, it's always possible to construct a symmetry-enriched topological order on the boundaries realized by finite gauge theory. And we can prove that for such a construction of gapped boundaries, actually generalized to the wider class of SPT phases, which can include the fermionic SPT phases. And for the Gouin SPT phases we have talked about, such a construction of gapped boundaries explicitly done by Lattice construction of Gouin phases in the presence of the gapped boundaries. And about the fermionic phases, so far the explicit lattice construction for the gapped boundaries is obtained by only for the Gouin phases, but I believe that most fermionic phases based on the finite symmetries can admit the gapped boundaries. It's just my intuition, but it's interesting to explore the problem in this direction. So before talking about the fermionic phases, let's recall the construction of the gapped boundary for bosonic case following the one-way term. For a given SPT phase protected by finite unitary symmetry G, the strategy for the construction of the gapped boundary, symmetry preserving gapped boundary is to prepare a specific symmetry extension of G by finite group K, and the extended group is denoted as H. And then here's the intuitive description for the construction. First, let's think of our GSPT phase as a SPT phase protected by extended group H by thinking of G symmetry transformation as a part of H transformation by lifting the group using the symmetry extension. And now let's assume that the SPT phase becomes trivial once we regard the theory as a HSPT phase. But then such a lift is turns out to be useful for the construction of gapped boundary. Intuitively, we consider the bulk of the GSPT phase and regard the right part as the HSPT phase. Then the right part can be trivialized by the H-symmetric deformation, H-symmetric unitary quantum circuit. And after this process, we get the H-symmetric gapped domain wall between the trivial and GSPT phase. And finally, in order to so at this point the symmetry of the domain wall is extended group H, but we want to make the symmetry G rather than H. So we gauge the K subgroup of the full H symmetry on the domain wall, which results in the G symmetric gauge theory, which lives on the boundary of the SPT phase. And this is a rough explanation for the gapped boundary of the GSPT phase. And in order for the in order for such a construction to be possible, of course, we have to make sure that it's actually possible to find such a group extension which can trivialize a given SPT phase. So we can see this by using the theorem proven by Tachikawa. It says that for a given group cohomology that represents the bosonic GSPT phase, there actually exists a finite group extension which makes the group cohomology trivial after lifting the group to H. So so after lifting the group, Y is actually trivial as a cohomology. So we can write this cohomology. We can write this Y as a derivative of some cochain. So then it's a simple matter to write down the boundary action. So we can just prepare the cochain X whose derivative becomes the SPT cohomology Y, and the action is given by integrating X on the boundary. And this uses H symmetric theory, but we can gauge the theory by summing over the K-sub group. So the integration of X just gives the construction of boundary. And by using the similar strategy, we can show that the arbitrary Gouin phases, arbitrary Gouin fermionic phases predicted by a finite symmetry, which can include the time reversal symmetry, admits a symmetry preserving Gibbs boundary. The Gouin phase is given by a pair of homological data subject to the Gouin equation. And then by basically using the theorem by Tachikawa, there exists a finite symmetry extension which makes these two Gouin data trivial when pulled back to the larger group H. And once we lift the group G to H, both cochains N and Y are written as the derivative of some, basically written as a derivative of some cochain. So we find some group extension which can bring this Gouin data into some trivialized form. And after lifting the group H, it has a form of this, basically written as a derivative of some cochain up to some additional term which is introduced to satisfy the Gouin equation. And given such a trivialized Gouin data, we can explicitly provide some lattice definition for the capital boundary of the Gouin phase. And this is done by extending the lattice definition of the Gouin phase to the case with the boundary. And so by slightly generalizing the Grassmann integral to the case with a boundary, so we call it as a bulk boundary Grassmann integral, and it gives the boundary action of some K-gauge theory coupled with a bulk, which is just done by mimicking by slightly generalizing the construction by one-way midterm to the fermionic case, and by using the bulk boundary Grassmann integral. And for the detail of the construction, you will see my work with counter and UG. Maybe in the Hamiltonian description is written in a very nice work by Yuan with Tyler and Nat. So we can actually construct the capital boundary for the Gouin phase using the Grassmann integral. So I want to talk about another application of the Grassmann integral. So I want to refer to the application to the 1+1 dimensional topological superconductor, which is classified by Z8 in the presence of the time reversal symmetry. The corresponding space-time structure is P minus that corresponds to time reversal squares to 1. And it is expected that the path integral of the corresponding field theory on the real projective space RP2 gives the phase quantized as Z8, and this phase diagnoses the classification. And actually, we can readily construct a lattice field theory generating such a Z8 classification by using the Grassmann integral on unrelated spacetime such as C2. To do this, we prepare the Grassmann integral, which is coupled with the P- structure, and so this theory coupled with the P- structure is not anomalous. So we can gauge the Z2 symmetry. So here the alpha is the background Z2 gauge field, and in 1+1D it's just a background gauge field is usual ordinary Z2 global symmetry. So we can gauge the Z2 symmetry by summing over all configurations of the Z2 gauge field. Then the gauge theory actually corresponds to the K-type wire generating the Z8 classification. So this is, for example, seen by so actually if we evaluate this partition function on RP2, we get a value that is proportional to 1 plus I. So in the case of the RP2, this sum runs over 2 terms, which is the trivial gauge field and the non-trivial gauge field of RP2, and the both term splits the 1 and I respectively. And then, so because this value is 1 plus I up to some amplitude factor, and this phase gives a S root of unity. So we find that it actually gives a theory for the generator of the Z8 classification. And the interesting application for the path integral of such a 1+1 dimensional topological superconductor is finding and understanding all the parameters that can diagnose the Z8 classification for a given ground state wave function. Concretely, we prepare a wave function on a ring, and I want some operation measured on the wave function, which can compute the Z8 index of the given ground state. So since the Z8 phase is associated with a path integral on an unrelated manifold RP2, so this operation should have something to do with the unrelated nature of the spacetime. So here let us introduce some interesting proposal by Shaporian and Shiozaki and Ryu for a reduced density matrix of the which is given from this ground state on some subsystem. They defined operation which is called the partial time reversal. Before talking about the precise definition of the partial time reversal, we note that this operation is analogous to the partial transpose on the Hilbert space, which takes the transpose of some fraction of the subsystem I1 of I. So we are taking some reduced density matrix on some subsystem, and this has something to do with some partial transpose, which takes a transpose on some Hilbert space on the subsystem of the I. And the transpose reverses the order of Brun and Ket. So this is regarded as changing the time order of the spacetime. So it's kind of operating the time reversal on some fraction of the system. Then they introduced such a operation and computed the trace of the reduced density matrix and the partial time reversed one, and they numerically computed it for the ground state of the K-type wire. And then they observed that the phase of this value is quantized as a S root of unity and detects the Z classification of the K-type wire. And so such a computation result is shown in the blue dot in the figure, and which computes the phase of the partial time reversal on the trivial and the topological phase of the 1+1 dimensional topological superconductor.
So this partial time reversal is defined to be partial transpose?
It's slightly different. Yeah,
What's different about it?
as I took later, but yeah, it's slightly different, and the main difference is something to do with plus and minus sign factor in the Grassmann integral. So yeah. So it's associated with operating the some such a fractional sign factor on the Grassmann variables on the some fermionic Fock space on I1. So it's slightly different with the partial transpose, but it's associated with this operation. So let's see how the partial transpose is associated with the geometry of the unwanted spacetime. This figure is a geometry that represents the reduced density matrix of the subsystem I. The reduced density matrix is regarded as a path integral on the disk geometry. So, so the boundary of is a subsystem I, and its orientation reversal, and it's regarded as kind of the Bura and Ket. And then the partial transpose acts on the fraction of the subsystem, and which is represented as a red curve, and it reverses the orientation of it since the transpose flips the role of the Bura and Ket. So it acts as kind of like a orientation reversal on this red line. Then if you evaluate the rest of these two objects, we end up with one cross gap induced on the spacetime because we paste these two geometries with orientation reversed along the red curve, so which results in effectively introducing the cross gap. So the resulting spacetime should be real projective space. So now let's introduce some precise form of the partial time reversal on a fermionic Fock space. This is partial time reversal is transparently expressed as in terms of the coherent space basis of the Grassmann variables. So because of the transpose on the subsystem I1, so this operation flips degrees of freedom on Bura and Ket of I1. So we are expressing the status of some sequence of the Grassmann variables, and the partial time reversal acts on I1, which basically transposes the degrees of freedom in I1. But moreover, we note that the minus sign factor is introduced. This factor is naturally in the original paper by Chaborian Shosaki-Ryu, this factor is naturally introduced by requiring that the torus is invariant and the partial time reversal, because so it flips the order of the chi and xi, and so this operation doesn't preserve the torus, but after introducing such a minus I psi factor, the anti-commutativity cancels out, so it's defined as a some operation which makes the torus invariant. But then, no, what I want to understand why the torus of the partial time reversal with some original reduced density matrix works as a order parameter of the Z8 classification from the path integral point of view I have formulated. To do this, we compare the definition of our order parameter with the unoriented path integral we have formulated. In the path integral point of view, the plus and minus I sign factor in the partial time reversal is counted when the Grassmann auto state is acted by the orientation reversal. So we are saying the same thing. So basically counts. So this such a sign factor minus sign factor is basically counted when the some Grassmann auto state is living on the cross gap, which reverses the orientation. So actually, this sign factor is exactly what we have introduced when formulating the unoriented Grassmann integral. So in this case, we also incorporated such a factor on the orientation reversing defects. So, and actually we can make the relation between the order parameter formulated from the partial time reversal and the Grassmann integral more precise if we start with a ground state that is given by the Grassmann integral. For example, we can consider some P minus we can start from some P minus topological theory for the Kita wire given by Gaussian the zeta symmetry of the Grassmann integral. Then we can obtain the ground state on the ring by the path integration on the disk. Such an expression gives you a state defined on the fermionic Fock space. And I don't explain here, but we can check that such an obtained state from the topological theory is actually the ground state of the Kita wire defined on the Fock space. Then we can prove that the order parameter is precisely expressed as a path integral of our theory on RP2 in the sense of the P minus topological field theory we have studied from. And hence, it gives S-reutability as I computed. And we can further extend such a correspondence to the more generic P minus theory given by the Grassmann integrals, and the interested reader can look into our paper. How much time do I have? Maybe already exceeding.
Yeah, you're already 11 here. So
yeah. So okay. So yes, maybe I should stop here. So the summary, as the summary for my talk is, I have formulated the local path integral for the GUN SPT phase, including the case unlimited case, and this is particularly useful for the formulation of the time reversal topological phases. And we have constructed the symmetry preserving TKFT of the symmetry preserving topological order on the boundary of the GUN SPT phase with a finite symmetry. And such a formalism is also used to diagnose the Z8 classification of the 1+1 dimensional topological superconductor. And I didn't explain, but I also have some work on the some 3+ dimensional topological superconductor using the which can generate the Z8 classification in C16. And the future work, maybe it's interesting to construct a gapped boundary for the beyond GUN phases, beyond GUN fermionic phases. Or I'm recently interested in generalizing such a construction of the Grassmann integral to the not the fermionic phases, but some ZR parafermionic phases. Maybe it's useful to formulate some parafermionic theory and develop some way to bosonize or parafermionize the theory. And it's maybe interesting to generalize for such cases. And that's all from me. And so thank you very much for attention.
yeah, thanks for Ryohei's nice talk. So it's time for question. So please ask question.
I have a question. This Z8 order parameter that you showed for 1+1D.
Yeah.
Do you know, like, have you thought about generalizing that to the 3+1D, like topological insulator in class A2 or whatever, which has U1 charge conservation and time reversal symmetry?
Yeah, maybe.
There you want the path integral on RP4, I think.
Yes. So it has something to do with some partial reflection or some partial inversion or something, and it's also considered by these people, but
no, they couldn't do it. I mean, well, my understanding was Shinsei, at least Shinsei told me that they didn't know how to do the case of the 3+1D class A2 topological insulator using these methods. So what I'm wondering is if you have maybe some additional insight perhaps on where this comes from using your topological field theory and Grassmann integral. So
yeah, maybe, yeah, you have something to do
thought
with
about the 3+1D1 and whether maybe one can make some progress there.
Yeah. Maybe it has something to do with orientation partial orientation reversing, and then additionally some sign factor on the orientation reversing. Yeah, but yeah, maybe it's interesting to consider.
Yeah, I have another question. So it seems to me that your approach worked very well for the 1D, so you can characterize the OZA classification. But for
sorry.
You say you can construct the OZA phase in 1+1D, but in 2+1, so let's consider the Z2 times Z2 F symmetry. It's also
2 plus 1D.
Yeah, 2+1D with Z2 times Z2 F symmetry. So the classification is also ZA. So the physical picture is quite simple. You just decorate the K-type chain on the Z2 domain. But as my knowledge, this ZA phase cannot be characterized by the Guwen supercohomology. So what's the difference here?
So basically, I don't have the good understanding of this ZA to root phase using the Grassmann integral. So so in the paper by Gayotan Kapustin and Laksha Bhardwaj, there is some expression of the some ZA to root phase using the some Grassmann integral coupled with some Ising-like field theory. I forgot, but
there's like a geometric correspondence, like so this Z8 root phase in 1+1 dimensions is like this ARF invariant. But in 2+1 dimensions, it's like you have like the spin group with Z2 gauge fields. That's the relevant structure group. And you're on like a Z2 domain wall. You're basically looking at like the ARF invariant of the of the domain wall. There's like some induced pin minus structure.
You're correct. So Z root phase is understood as some decorated domain wall picture, and it's schematically written as some Z2 gauge field cup Brown invariant based on the P minus structure, and so I think the Bhardwaj Gayot Kapustin has expressed this phase using the Grassmann integral in the sense that we couple some bosonic theory with Grassmann integral and gauge some Z2 symmetry, but I forgot how they did it. I don't understand how they did it, but
But I think in the original Guwen 1's paper, they only give the Z for classification.
I think so. Because the clear phase is Z for subgroup.
So why are they missing the Z2 factor? Is it from the spin structure or somewhere else?
Sorry, what is Z2 factor?
I mean, they only give the Z4, right? So they miss some Z2 structure. So
Z2 comes from some type Y decoration. So there is some layer of the which can to express the fermionic SPT phases. So the most easy layer is a bosonic SPT, and the second easy layer is a Guwen fermionic SPT. So it has two data of cohomology, but the third layer is more difficult. It has something to do the decoration of the Kita wire, and the way to decorate the Kita wire is controlled by the another cochain data, and we have also some complicated Guwen equation which correlates these three cohomology data, and we can also go higher, which can decorate the P plus IP superconductor or something. But such a Z2 factor comes from the extension of the Guwen data by the way to decorate the Kita wire.
Thank you.
I have a question about the way you constructed a gap boundary that preserves G symmetry by
Yeah,
considering a larger group H and then gauging out subgroup K.
yeah.
Just so I understand, if G is taken as, say, U1 charge conservation symmetry, then what is the H that you would consider?
So I'm considering the finite symmetry. In the case of the continuous symmetry, it's not guaranteed to the possibility of preparing the symmetry extension, which trivializes the cohomology data, is not guaranteed. It's not guaranteed, so it's not possible in this case. But yeah, maybe yeah, I'm not sure about
Okay.
we can
So
think of,
supposing I considered, say, a Z2 symmetry or some discrete subgroup of U1, then what is the H? That you would
maybe yeah, we can think of the extension of U1 by Z2, which can be either U1 or U1 times Z2, whether it's trivial extension or non-trivial extension. Yeah. But I'm not sure we can construct gap boundary using such prescription.
Okay, thanks.
Yeah. It's very interesting to ask if such a prescription is possible for continuous symmetry group. So for the case of the there is some cases. So in the case of the some oriented gravitational anomaly, we have the action is typically expressed as using the second stable photonic class, and we can trivialize such a stable photonic class by lifting the symmetry to spin. So if you start from some bosonic phase, which is based on SO of something, if the boundary admits a spin structure, we can trivialize such a action for the gravitational SPT phase by extending to spin using the T2 symmetry, and it actually gives a construction of gap boundary for the, for example, W to W2 phase. And on the boundary, we have some 3-fermionic topological dot state, and it gives some construction. But in general, we don't know how to do that. Yeah.
Any more questions? Myself, you are mute.
Yeah, sorry. I was just wondering, do you have any comments on whether one can get the generator of the Z16 via an exactly solvable model? Like, do you think do you think it's not possible?
I saw some discussion on Facebook feed. I think it's not possible because I have something to do with decoration of P plus IP superconductor. So
I think the thing that surprises me is that, I mean, you have also this paper where you work out this like way of calculating the Z16 anomaly. Using these like grain getter gluing constructions that we had done earlier for the boson case.
Yeah, I'm assuming that we have done some. Yeah, I tried to derive this formula by coupling with some Waka-1 model with the Grassmann integral. And just use some, just compute this partition function on RP4 using some gluing relation of Waka-1 model. But I'm not sure whether we can construct the.
But if there's a gluing relation, if there's a way of getting it from gluing, then there should be a way of getting it from a state sum. And then if there's a way of getting it from a state sum, there's usually a Hamiltonian that comes along with state sums.
Yes, that's mysterious.
So from that perspective, it seems like there should be a way of getting the generator of the Z16 from the exactly solvable model.
I have a quick question. So the Fikowski and Kopstein, they prove there's no commuting projector Hamiltonian for Cairo, for the 2D Cairo phase, right? Does this imply that the 3 plus 1D, the Z16, we decorate P plus IP, this cannot be constructed from the commuting projector Hamiltonian?
I don't see why it proves that.
Because like people's IP is some chiral 2D phase.
So
Yeah, but then wouldn't the generator of Z8 subgroup correspond to decorating 2 P-plus IPs, or no?
Yeah, let's go for it.
yeah.
Maybe like the bulk sort of allows you to escape that proof.
Right.
So can you prove the impossibility to construct a commuting projector model using such coupled infinitable scale argument? For example, using the dimensional reduction approach. So we start from some 3+1 dimensional geometry with time reversal defect and shrink the geometry to effective 2+1 dimensional model, which has some for conductivity, which is not possible, or something like that.
I don't see how to do that, but I don't know. But I mean, I'm a bit confused. Like, there is a state sum for the Z16. Well,
yeah.
no one's constructed it yet, but I mean, the closest
I haven't
thing is
constructed
your work. The closest thing is your work where you glue together these like generalized Crane-Yetter things for the fermionic case.
Yes, so maybe we can start from some SO3 or 3 topological, some workout model and try to put such a workout model on the unoriented manifold and couple with the Grassmann integral. Yeah, if we work the whole things out, yeah, maybe we can construct some path integral. But, yeah, I haven't done that. I haven't done so expressed construction. Yeah.
Okay.
Yeah.
So any questions? So if there's no questions, then let's send for Ryohei's talk today. Yeah.
Yeah. Thank you for attention.
Already 1 a.m. in Japan, right?
Yeah, but yeah, no problem for me.
Okay. Thank you.
I'm usually staying up late.
Thank you for your talk.
Yeah. Good night.
Yeah. Thank you. Yeah.